Hello everyone, welcome to Dev Summit. My name is Sheng-An Zhan. I'm a product engineer on the Raster team. In this demo, we will discuss the set of tools and APIs in ArcGIS Pro Image Analyst extension that are focused on the prediction and trend analysis of multidimensional raster data. I will briefly introduce some concepts relevant to this demo theater. Then I'll talk about the prediction and trend analysis capabilities in ArcGIS Pro. Finally, I'll go through two demos to show you how this works using ArcGIS Pro interface as well as using ArcPy. First of all, what is multidimensional raster? Traditionally, a raster contains two dimensions, x and y, which describes the location of a pixel. A multidimensional raster is a raster data that contains more than two dimensions. It includes dimensions such as time and depth. It can also contain multiple variables such as temperature, precipitation within a single raster. Examples of a multidimensional raster include a 3D array that contains multispectral satellite imagery of a location across time. It can also be a 4D array that stores not only the ocean temperature across time, but also across different depths as well. Multidimensional data is especially relevant today because with the data boom, we're not only collecting information about what happened where, but we are also increasingly interested in when it happened, how it has developed, and how it will change in the future. Having multidimensional data adds a key component, time, to our analysis. ArcGIS Pro supports many multidimensional raster formats. The ones we are going to see today are Cloud Raster Format, CRF, and NetCDF. CRF is the default output format in ArcGIS Pro. It supports multiple variables, dimensions, as well as processing templates. Its storage is divided into small bundles of tiles, so it is optimized for distributed processing. NetCDF is the community standard for sharing scientific data. It is portable and machine independent. ArcGIS Pro also supports other formats such as HDF and GRIP. Once we have some multidimensional raster, we can use trend analysis to understand what has happened in the past and predict what will happen in the future. In trend analysis, we fit models, such as one from here, to describe the data along a dimension, such as time or depth. We can then predict values in those dimensions to understand what happened outside of the scope of the original data. We have two sets of functionalities that can be used to conduct prediction and trend analysis. The first set is geoprocessing tools, also known as GP tools. They are generate trend raster and predict using trend raster. GP tools will generate output files that contain the result. We also have raster functions, generate a trend, and predict using trend that does the same job as the GP tools, but these raster functions do not save results to the disk, so they can process images on the fly and are very fast. We can also conduct these analyses programmatically using ArcPy APIs. And these are the corresponding APIs to the GP tools as well as the raster functions. Trend to RGP and temporal profile are helpful tools that can be used to conduct analysis on the results as well as visualization. A typical workflow on prediction and trend analysis is as follows. First, we create a multidimensional raster. Currently, we support Cloud Raster format as well as scientific formats such as NetCDF, HDF, and GRIP. Then we generate a trend raster from the input. Depending on the characteristics of the input data, we can choose to generate trends using linear, harmonic, polynomial, man candle, and seasonal candle methods. Then we can use the trend raster to predict values along different dimensions, such as time and depth. Finally, we can use the temporal profile tool to visualize results of different variables at various locations, depth, dimensions, and bands. Now I'm going to show you two demos. The first demo is modeling and predicting sea surface temperature variability. This demo will be done using the ArcGIS Pro interface. I will use both GP tools and raster functions. Here I loaded a sea surface temperature dataset from the Climate Forecast System Reanalysis product. This is a monthly dataset that covers from 1980 to 2015, as can be seen from the multidimensional info tab here. In order to better visualize the data, we can create a temporal profile. This is a useful tool to visualize the data along certain dimensions, and in this case, it is time. Let's say we're interested in the ocean temperature along the coast of Los Angeles. We can select a pixel over here along the coast, and you will generate a time series of the monthly temperature from this pixel. Then we can open up the Generate Trend Raster GP tool to model the trend. Set the sea surface temperature layer as the input. And since this is a monthly data set, and we can clearly see a cyclical pattern, I will set the trend type to be harmonic so that we can capture the seasonal cycle. And I'll leave the rest as default and hit run. After the tool finishes, we can see the resulting raster containing the regression coefficients for the slope, intercept, as well as the harmonic components of the regression. This layer here shows the slope. Areas in purple have experienced increase in sea surface temperature over the past 35-year period, whereas areas in green have experienced decrease in sea surface temperature during this period. Then we can put this layer into the predict using trend raster GP tool to predict the temperature for time slices that we are interested in. Here I want to predict the monthly temperature from 2016 to 2019. So I will set the definition to be by interval and the start date to be January 1st of 2016 and the end to be December the 1st of 2019. And the interval will be 1 month. And hit run. Now we can see the predicted output. Similarly, we can create another temporal profile for the output. After locating to the same place, we can see that the prediction indeed captures the cyclical pattern of the temperature between 2016 and 2019. Now, I'll repeat the process using raster functions and extend the analysis a little bit. Here we have the same input data. If we go to Imagery, Raster Functions, we can find the Generate Trend function under Analysis. Similarly, we set the input to be the sea surface temperature dataset and the trend type to be harmonic. And this time, we also check R squared and the p-value of slope coefficient to include them in the output. Here, we can see the same slope raster as before. We can also use the R squared and p-value bands to evaluate the accuracy of our regression model and to find locations that have experienced statistically significant changes. The R-squared value shows how much of the variance in the data can be explained by the model, and the p-value shows how significant the fitted slope is. We can use the mask function under data management for this task. The mask function allows us to set ranges of values that we want to keep in the output. From the generated trend raster, we see that R-squared is the 6th band and the p-value is the 7th band. Let's say we want to see the regions where the R-squared value is greater than 0.8. We can set the minimum for band 6 to be 0.8 and the maximum to be 1. And for the 7th band, the p-value, we can set the 7th item to be between 0 and 0.05. To only include the pixels that have a significance value of 0.05 or below. We can now navigate to the R-squared band in the mask raster and to see the regions that have a value of greater than 0.8, which is in color here. We can also switch to the p-value band to see the regions that have experienced statistically significant changes. Another way to visualize the trend is using the trend to RGB function. This is under conversion. Set the generated trend raster as the input and set the model type to be harmonic. Before we create the new layer, I want to briefly talk about how the harmonic coefficients are visualized. This slide shows the harmonic regression equation as well as how the coefficients are transformed to be visualized in red, green, and blue. On the top here is the equation of the harmonic regression. Beta 0 is the intercept, beta 1 is the slope, beta 2 and beta 3 are the harmonic coefficients for cosine and sine. Beta 2 and beta 3 are used to calculate the amplitude as well as the phase, which are then used as inputs to the hue, saturation, and value color model. The amplitude decides the saturation of the color. A larger amplitude means a brighter color, while the phase decides which color it is. And the value here is a constant. This model is then converted to RGB for display. So in our trend to RGB results, regions with high saturation, such as here and here, are locations that have high amplitude, meaning that they have high variability. Blue and yellow are complementary colors. This means that the regions in blue and regions in yellow are in opposite phases, which makes sense because of the opposite seasonality between northern and southern hemispheres. Finally, we can predict the sea surface temperature using the predict using trend function. We set the generated trend raster as input and set the definition by interval and set the start and end dates to be the same as before. The interval would be 1 month. Now you can see the predicted raster. It is a monthly raster from 2014 to 2019. And we can also create temporal profiles and check the predicted result. In the second demo, I will show you how to do similar analysis using the ArcGIS APIs to model and predict urban growth using nighttime light imagery. This Jupyter notebook shows the full workflow which can be run directly in ArcGIS Pro. First, we need to import ArcGIS, NumPy, and check out the Image Analyst extension. Then we load our multidimensional raster containing the nighttime light data into a raster object. The true argument here specifies that the raster is multidimensional. We can see that the variable here is called nightlight data, and we have 22 slices. Here we can see that each slice is an annual composite for that year, and it covers from 1992 to 2013. We can use the arcpi.ia.subset function to create a subset of the data for visualization. I'm showing the nightlight data for 1992 using the arcpi.ia.render function. The brighter a pixel is, the more light there is, and is more likely to be an urban region. Because this is yearly data, we fit a linear trend to the input. Here I used arcpi.ia.generateTrend, which is a raster function. This is faster than the GP tool because it doesn't actually save the output. I specify standard time as the dimension so that it knows the fitting will be done a long time. The regression type is set to linear for a linear regression. If we want to save the result to disk, we can call the .save method on the raster object. The resulting trend raster contains the regression slope and intercept for each pixel. In order to better make sense of the trend raster, we can call the trend to RGB to convert the trend raster to a 3-band raster. Pixels with positive slope is assigned to the red band. Pixels with negative slope is assigned to the blue band, while the intercept is assigned to the green band. This is much more simpler than the harmonic type. Then we can render the RGB image here. We can now easily see that areas in red are areas that have experienced an increase in night lights, such as in China, India, and parts of South America, while areas in blue have experienced a decline in night lights, such as in parts of Japan and Russia. Areas in green have remained stable in night lights, such as the majority of the US. We can then use the arcpi.ia.predictUsingTrend, which is also a raster function, to predict nighttime light values on any specified dates. Here I use the by interval type and set the start to be January 1st of 2014 and the end to be January 1st, 2019. The interval is 1 and the unit is years. This means that I wanted to create a prediction on January 1st of each year from 2014 to 2019. Here it shows the results consist of 6 rasters, which is as expected. I render the results here, and I can also save the prediction to disk using the save method. Then we can conduct some analysis on the prediction. Let's say we are interested in how much urban area has grown between the start of the data, which is in 1992, and the end of our prediction, which is 2019. We can subset the 2019 image and set a threshold to it. Let's assume, based on some exploration of the data, that pixels that have a value greater than 50 is urban. Here I'm using the thresholded image. It looks similar to the previous result, but this is a binary image containing of only zeros and ones. Then we can calculate the number of 1 pixels in the output to estimate the total urban area in 2019. I do this using the arcpi.ia.pixelBlock This function allows us to iterate through the pixels in an image block by block. So for each block, we can count the number of pixels that equal 1. Since the data is in 1 kilometer resolution, the number of pixels roughly equals the total area. We can see that in 2019, we estimate the total urban area to be about 1.5 million square kilometers. If we do the same calculation for 1992, we can see that the area is close to 800,000 square kilometers. So we can see that the total urban area almost doubled in less than 30 years. This is a relatively simple analysis with simple assumptions. You can also use more complicated thresholding algorithms or divide the image into continents to study it in more details. But this example just shows you how you can conduct trend and prediction using multidimensional raster in ArcGIS, and the possibilities are endless. That sums up this demo's theater. If you'd like to learn more about raster capabilities in the ArcGIS platform, please join one of the following sessions and refer to the help references on our website. Thank you for your attention, and please provide your feedback for this session by clicking on the session survey link below this video. Have a nice day and enjoy Dev Summit.